instead of going for slides and stuff, let's get started with standards. There are two standards which are there for IEEE for R plus studies. One is IEEE 1584. This is an IEEE guide for performing arc flash hazard calculations, how to perform arc flash hazard calculations. And the second one, this year IEEE 1584 is 2018. The original came in 2002, then like means to say amended in 2004, then like means to say they came up with some more addition in 2011. But like means 2002 to 2018, like there is a huge change. So it completely upgraded. It came about like 8 years back. And later, IEEE 1584.1, which came, this gives like guide for specification of scope and deliverable requirements for an R plus hazard study calculations in accordance with IEEE 1584. So both the standards are important. So means we will go through, like I mean to say, going through both the standards, then go to the slides, then come for a simulation in SKM, then we will wind up our sessions. So let's start with IEEE 1584. So what it covers and what it not covers, right? So this is a title page, then like important notices who are all contributed to this, and an introduction, content, right? Content, then list of figures, list of tables. Here is where we have to start about. So this IEEE guide for performing arc flash hazard calculation, IEEE 1584 2018. This provides models and analytical procedure, right? This provides model and analytical process that enables to predict the incident energy and R flash boundary. So IEEE 1584 only helps you to get incident energy and R flash boundary. Recommending personal protective equipments PPE is not part of IEEE 1584. For that, you have to go for NFPA 70E. If that is clear, just put CC in chat. IEEE 1584 gives you only the model and analytical process to find out the incident energy IE and R flash boundary AFB. It is not recommending PPE. In order to identify the PPE, you have to go for NFPA 70E. If that's clear, just put CC in chat. Yeah, thank you, Soumya, for putting full length crystal clear. Cool. So then like means to say what it includes, what it excludes. So this IEEE 1584 covers in detail collection of data. Data collection is included. Considering power system operation scenarios, like two incomers bus coupler open, one incomer failure, bus coupler closed, like means to say grid operation scenario, diesel generator operating conditions, etc. Like it considers data collection, considering the scenarios as well as the calculation parameters. But we need to understand the limitation of the standard. This is applicable only for three-phase alternating current. It is not applicable for a single phase. It is not applicable for a DC. IEEE 1584 is applicable only for three-phase AC system from 208 volt to 15 kV. The many people thinks then like means to say, it means like there is no R plus study needed more than 15 kV or less than 208 volt or a DC system or a single phase system. Answer is no. This IEEE 1584 is applicable only for three-phase AC system between 208 volt to 15 kV. So single-phase AC system or a DC system is not part of this guide. That doesn't mean you need not perform or you should, like means you can leave as it is. For a DC, of course, nowadays solar has grown, battery energy storage system has grown more than 15 kV, like live maintenance we are doing. So there also R plus study is needed, but this standard is not applicable for that. If that is making sense, just type MS in chat. Because many people think that, like, means to say, more than 15 kV R plus is not needed. It is not so the case. The standard is applicable only from 208 volt to 15 kV, three-phase AC system. The standard is not applicable for a DC. The standard is not applicable for a single phase, but still you need to perform this R plus study wherever it is needed. So calculation for a single phase AC system, DC are not part of this, but some guidance and references are provided. Recommendation of PPE is to mitigate is not included in this guide. PPE is not included in this guide. It is very clear. So what's the purpose? This guide is to enable qualified persons. It is not defining who is a qualified person. There are many people thinks that like there is a certificate needed to perform an R plus study. There is no such certificate recommended by IEEE, but it says enable qualified persons. The qualified person should be a power system engineer. He should have done short circuit study. He should have done like relay coordination. Then probably like he should have done R plus. That's probably like kind of a qualification which we can talk about. To analyze the power system for the purpose of calculating the incident energy to which employees could be exposed to during the operation and maintenance. So when you are doing an operation and maintenance in your system, what's the incident energy which the employees are exposed to? That's probably the standard talks about. So who is responsible? Contractors, facility owners, like means to say, they can use this information to help provide appropriate protection for employees. The facility owners or the contractors should provide appropriate PPE by means of performing R plus studies, finding out the incident energy, R plus boundary, and probably referring to NFPS 70 proper PPE. So, like IEEE 242, like I mean, so say that's for a relay coordination, and 551, that is for a short circuit. For that matter, like you can refer IEC 60909 as well. IEEE 1584.1, now like 2022 document, and C37, that is AC high voltage circuit breakers. These are all cross reference. So one is short circuit, other one is a relay coordination, because short circuit and relay coordination becomes essential input for an arc flash. When we talk about an arc flash, we are talking about I square T. I is a short circuit current or an arc current. T is the fault duration or the arc duration. So I square T, arc current that comes from the short circuit, and arc duration that comes from the relay coordination. You essentially need to have two important aspects. One is a short circuit study. Second one is a relay coordination. These are all two important aspects which you have to be thoroughly aware of before jumping into arc flash studies. Without short circuit study, without relay coordination, nowadays many peoples in the market, they are performing arc flash studies, which is of no meaning. That's the reason why I'm saying. There are people without performing short circuit studies, without performing a relay coordination studies, they are performing an arc flash studies in the market. You need to understand incident energy arc flash boundary is the product of short circuit, which gives you the arc current. Relay coordination that gives you the arc duration that results in, like I mean to say, arc flash study. You cannot perform arc flash study without understanding short circuit and arc flash. Sorry, short circuit and relay coordination. So the standard reference is given, IEEE 551, that is for short circuit, which you can refer IEC 60909 if you are from IEC world. And then probably like means to say 242, that's for a relay coordination. Then like IEEE 1584.1, that is guidance. C34, that's for high voltage circuit breakers. So there are some general definitions which are given, right? So we are in 3. So general definitions: what is arc, what is arc current, what is arc duration, what is arc flash, what is arc flash boundary, arc flash hazard, all those things which is given. What is arc? Arc is a plasma cloud. This is formed in gap between two electrodes with a sufficient potential difference. I have two electrodes, electrode 1, electrode 2, with a sufficient potential difference. That means this is at a different voltage, this is at a different voltage. There is a plasma which has been, like means to say, formed between these two. That means the current is flowing via this. So that's probably an arc. That's a definition which is given in IEEE 1584. What is arc current? Which is also an arc fault current. During this arc, what's the current which flows? That's arc current. What's the arc duration? This is the fault clearing time. We will see in the definitions. What is arc flash? This is an electric arc event. The event has happened, arc event, which emits a thermal energy. And this thermal energy is dissipated in a, like I mean, as a radiant, convective, and conductive heat. So obviously, when you have a heat, that heat has to be dissipated in 3 forms: conduction, convection, and radiation, and all the 3 forms. What is arc flash boundary? What is arc flash boundary? When there is an arc event which has happened, like means to say, it probably with respect to the place where the arc has happened, with respect to the distance, this arc impact will keep coming down. At what distance it has reduced below 1.2 calories per centimeter square, that's called arc flash boundary. That means where the arc has happened, the incident energy is extremely high. With respect to the distance from the arc, the incident energy will keep reducing. At what distance the incident energy comes below 1.2 calories per centimeter square, that's arc flash boundary. So what is arc flash hazard? It is a dangerous condition associated with an electric arc likely to cause possible injury and maybe a fatality. What is arc flash hazard calculations? Compute incident energy and an arc flash boundary. That is arc flash hazard calculations. If you look at what is the standard talks about this arc flash hazard calculation. So it, like, objective of the standard is only 2: calculating incident energy, calculating arc flash boundary. That's it. Like, you need to understand the difference between arc current and the voltage fault current. What is arcing fault current? A fault current flowing through the electrical arc plasma. What is voltage fault current? Like means to say, a conductor touches another conductor and the current flows. Here, there is no arc between these two conductors. Conductor face, say R face, Y face, touching each other, and probably there is a current which flows. This is a fault current. It is not an arc current, it is a fault current. So that is voltage fault current, in fact. What is arc current? I have a conductor, another conductor. Because of whatever may be the reason, there is an arc between these two. This arc offers a resistance. So means, let's say this is current which is going as an arc current will be less than the voltage fault current because of this arc, right? So that's an arc current, and this arc current is the current which is going between two electrodes, right, via this as a arc plasma. So available short circuit current will be obviously higher, arcing fault current will be less because that reduces due to the arc resistance. So available short circuit current, that's maximum short circuit current available. Voltage short circuit current without, like I mean to say, it's a zero impedance scenario. What's the clearing time? This is a total time between beginning of a specified overcurrent and the final interruption of the circuit at rated voltage. And event occurs, arc or a fault occurs, and from the instant at which it has started till the instant at which the current becomes zero. That's basically clearing time. So electrode configurations, like we will be seeing that, like, there are 5 different electrode configuration: VCB, VCBB, HCB, VOA, HOA. So vertical conductor with a barrier, horizontal conductor, like we have an image, we can see vertical open air, horizontal open air. There are like 5 different configurations. Based on the electrical configurations, the incident energy will be different, R plus boundary will be different. So these are all like means to say some definitions which you can go through, some acronyms, but like means to say, like let's try to understand. Means to say, the standard gives model for incident energy calculations, i.e., incident energy. It is empirically derived model. That means there is no mathematically developed model, but it's empirically derived model based on the statistical analysis and curve fitting problem. So this is applicable for 208 volt to 15 kV 3-phase. So it's applicable only for 50 hertz or 60 hertz. It is applicable only from 0.5 kiloamps to 106 kiloamps if the voltage is 208 volt to 600 volt. That means low voltage system, it is applicable from 0.5 kiloamps to 106 kiloamps. And 600 volt to 15 kV, it will be applicable for 0.2 kiloamps to 65 kiloamps. That means if it is 11 kV system has 80 kiloamps, a scenario, like the standard is not applicable. If you're talking about a generator circuit breaker at like 13.8 kV, which has like more than 65 kiloamps short circuit current, there this IEEE 1584 methodology is not applicable. IEEE 1584 is applicable 208 volt to 15 kV, 3-phase, 50 hertz or 60 hertz, 208 volt to 600 volt, 0.5 kiloamps to 106 kiloamps, 601 volt to 15 kV, 200 amps to 65 kiloamps. And this is a gap which needs, like, this are all, like, means only it is applicable in this because it's not a mathematically derived formula, it is an empirical formula with a statistical analysis and curve fitting programs is how this model has been developed. So this is developing a model for an incident energy calculations. So this model has been divided into 2 parts, right? So 600 volt to 15 kV, 208 volt to 600 volt, right? So what are the steps involved, right? So summary of steps involved. You need to find out first arcing current, B, arc duration, then to determine the incident energy, then find out the arc plus boundary. These are only 4 steps. Find the arcing current, find the arc duration, determine the incident energy I square T, determine the arc plus boundary. So what you need to understand is like means to say it's a simple 4 steps. Perform a short circuit current, find out the voltage current, from there derive the like arcing current. Second one, perform the relay coordination, find out the fault clearing time, find out the arc duration. From there, I square T, find out the incident energy. Fourth one, find out the arc plus boundary, the distance at which the incident energy comes down to 1.2 calories per centimeter square. So you will be having like multiple steps, like means to say range of model, model application overview, intermediate average arcing current variations, incident energy calculations, intermediate arc plus boundary, enclosure factor, IR, determining IR for 600 volt to 15 kV or like means less than 600 volt, single phase system and the DC system, they are giving some cross references, but they have not, like this entire model is only for a 3-phase from 208 volt to 15 kV. Like they have given for a single phase system and DC system also, they are probably given some guidelines. Applying this model, like means say, how do you apply this model? That's given. Now come to the actual steps. So what are the steps involved in performing an arc plus study? Step 1, data collection. Collect the data of the system, grid short circuit current, cable length, cable impedance, transformer rating, transformer impedance, operating. Then like means say decide system mode of operation. What is system mode of operation? Like means say only one source, two source with the bus coupler open, two source with the bus coupler closed, two source with the bus coupler open, and then one source fails, other source with the bus coupler closed, it's running. So step 1 is collecting the system data. Step 2, determine the mode of operations. If the grid completely fails, then like a diesel generator, like find out what are possible operating scenarios. Then third one, perform a short circuit study to find out the bolted fault current. Fourth one, determine the typical gap and the enclosure size. Then determine the electrode configuration. This is where we have discussed like there are five different configurations. VCB, VCBB, the vertical conductor with a barrier. So here you can see vertical conductor, here vertical conductor with a barrier. Horizontal conductor, obviously incident energy can be more because like it is directly coming front. Vertical open air and horizontal open air. So you have to find out like means to say electrode configurations. Then you need to find out the working distance. The working distance, if it is not known, this is a standard which gives you what's the working distance. So if like typically nowadays nobody is using any other working distance apart from the standard value, but like means to say if the working distance in the field is known, you have to use the actual working distance. R plus protection is typically based on the incident energy level on the person's head at the working distance and not the incident energy on the hands or arms. It is not on the hands or arms. It is on the person's head from the distance at which the instant like means that arc occurs. So typical working distance can be found in this table. So means say nowadays, as of my understanding, I have never seen customer gives this working distance. We are taking everywhere from this table only. It is 91.4 centimeter for 15 kV, 5 kV, and it is 61 centimeter for a low voltage switchgear, and it is for MCCs, distribution boards, etc. It is 45.7 centimeter. These are all three different working distance for like I mean to say this is low voltage distribution boards, low voltage switchgears, then medium voltage switchgears. That's it. Arcing current. Finding out the arcing current, that's the next step. Determining the arcing duration, that's from the relay coordination, arcing duration. Then calculate the incident energy. Then finally finding out the R plus boundary. And that probably like means to say concludes. And some of the cautions and like means to say disclaimers as a part of the standard. So that's probably like means to say what standards is talking about. Like means this is what the standard is talking about. And in addition to IEEE 1584, like you have to understand IEEE 1584.1. IEEE 1584 talks about it's a guide for performing R plus hazard calculations. That means it helps you to develop a model to find out incident energy and R plus boundary. And IEEE 1584, it is guiding for the specification, scope of deliverables when R plus hazard calculation is performed by a consultant and probably plant facility owner. What is bolted fault current? If it is not still clear, the fault which happens without a fault impedance is a bolted fault or a bolted fault current. Like RYB phase conductor is there, R phase is falling on the tree. The tree has a resistance. A conductor which is falling on the rock that has a resistance. So it is not a bolted fault. That is happening fault with a fault impedance. What is bolted fault? Without any fault impedance or arc between the conductors, and that is basically bolted fault. Right. So IEEE guide for specification for a scope of deliverables, it defines what is to be done by consultant and what are the deliverables as a part of an arc plus studies or arc plus hazard calculations. Rather than standard says arc plus studies, it says arc plus hazard calculations. Arc plus hazard calculations include two things, incident energy and arc plus boundary. So when coming to the standard, so what is to be done or what is the scope? It's all general. Like let's come here. Yes. Scope of this document, purpose, word usage, items not included in this guide. definitions, R plus hazard calculation study general guidelines, and system mode of operations, data required and collections, voltage fault current, arc durations, additional R plus calculations, and like means a study report. So this document gives you everything what you need. So please make a note. The standard provides a guidance for a specification and performance of R plus hazard analysis in accordance with IEEE 1584. So this gives a guidance and a specification. If somebody has to perform R plus hazard calculation using IEEE 1584. This defines a scope and specification. And purpose of this standard is to enable the stakeholders. Who is a stakeholder? A facility owner, probably a consultant, safety officer, who are involved. They are stakeholders to understand the minimum scope of work. Please try to understand it defines only the minimum scope of work. Over and above, facility owner or a consultant or probably safety officer can add more. It gives a minimum scope of work and deliverables required for an R plus study. So when facility owner appoints a consultant perform R plus hazard calculations as a part of this R plus study, what are the minimum deliverables which are required? Minimum scope of work and deliverables required. That's what the standard defines. So stakeholders are responsible for a personnel in facilities and installations with an electric energy as a potential hazard to employees and other personnel. Stakeholders includes but not limited to employers, owners, operators, contractors, as well as those who are responsible for specification or the performance of a study, which is a consultant. So would be an employer like IT company. He's an employer, but facility owner is somebody else. But employer, an IT company like Infosys or TCS, sitting in somebody's rental building. Owner is somebody, employer is somebody. Both are involved as a part of it. And probably like means to say, this employer might have appointed some third party for an operation and maintenance. That operator also included. And in case like some contractors doing the work, they are also included. And means to say who are responsible for like means to say specification and performance of the study. So item not included. Recommendation of PPB is not included. Recommendation of content of equipment label is not included. Recommendation for reduction in the incident energy is not part of the scope. Performing short circuit and relay coordination is not part of the scope. In the sense, like not included in IEEE 1584 and 1584.1. The following items are not within the scope of IEEE 1584 and therefore not addressed, but these are all mandatory as pre-step for performing an R plus study. Verification of data supplied by the owner, evaluation of the suitability of installed equipment versus applicable ratings, estimation of R plus hazards for a single phase or DC or the voltage beyond 15 kV. These are all not covered under IEEE 1584 and hence IEEE 1584.1. So definitions like the same definitions which has been given earlier. So 208 volt to 15 kV. So like I mean to say, Annexure B provides a checklist that may be used to help specify suggested deliverables. So as a part of IEEE 1584.1, there is an Annexure B. We will go through that Annexure B that provides a checklist. So the standard IEEE 1584, you need to perform short circuit. You need to have a protection device setting coordinations. You need to have a single line diagram. Short circuit IEEE 551, and you can instead use 60909. That is, if it is IEC 60909, like which you can use. Like means to say, you need to ask whether it is an existing system or probably a proposed system. In general, like people will ask within how many years you need to perform, R plus studies. It is not years. If there is some modification in the protection setting, or if you're modifying some equipments, like means you're adding a new motors, or you're adding a new generator, or you're modifying a configurations, R plus study needs to be performed. As and when there is a change in any of the equipment which results in change in the fault current or a fault clearing time, the R plus study needs to be performed. It is not years. It is not months, days, etc. As soon as you change something in the power system, which changes the short circuit current, what are the things which will change the short circuit current? If you're adding a motor, it will increase the short circuit current. If you're like means to say changing the configuration, it will change the short circuit current. If you're adding some circuit, it will change the short circuit current. If you're operating in a different configuration, keeping bus coupler open sometimes, and probably like means later you are deciding to change the configuration to bus coupler closed, it will have an impact on the short circuit current. So as soon as something changes in the configuration which have an impact on the short circuit current, your R plus study has to be revisited. And like means to say, you're changing something on the relay setting. Then also like means to say, you need to perform this R plus study. So when the R plus study has to be performed, any modification in your power system which has an impact on the short circuit current or a fault clearing time, you need to repeat this R plus study. Even if it is 100 years, there is no modification, you don't really need to perform an R plus study. Even after 100 years, nothing if you have modified, you need not really perform R plus study. But even it is just one day, if you have added a new motor, or if you have changed the configurations, or you have added an additional generator, or the grid short circuit MVA changes considerably, you need to perform an R plus study. Because most of the people will ask this question, like means within how many years you have to report. Like means see, R plus study is a desktop study. R plus study is not something on the field. You're going and testing. Means many people, those who are sending an inquiry to us will say, sir, how many days you will do R plus test at site? I'm not coming to site to do the R plus test live, right? I'm sitting safely in front of a desktop and performing R plus studies. And this R plus study is an outcome of right data from the field, right modeling in the software, and like means say defining all possible operating scenarios in a right way, finding out the worst case short circuit current which could be maximum or minimum, because the short circuit current of higher value may probably the fault clearing time will be extremely less, slightly lesser fault current, the fault clearing time could be much high. So you need to understand it is just not about the current, it is just not about the time, it is current and the time I square t that probably gives you the worst case. And like me to say, if you have like 100 switch gears in one configuration, maybe like 40 switch gears will have a worst case. That means like all the incomers are on, bus coupler closed. That could be the worst case for 40 switch gears out of 100 switch gears in your plant facility. And with one incomer fails, other incomer takes care of both the switch gears with the bus coupler closed. That would be the worst case for another 20, 30 switch gears. Grid fails, diesel generator is running, that could be the worst case for the remaining 30 switch gears. So you need to evaluate all possible electrical configurations in the system before concluding that, like I mean to say, incident energy and R plus boundary. R plus study, the cost is small, the risk is huge, right? R plus study typically how much? Maybe 3K to 5K dollars in a small industry. The cost is small, but risk is huge. That risk could be fatality as well. Like I mean, so say, save your colleague's life. You can probably put save your life also if you are doing an operation maintenance. If you are standing in front of the switchgear, you are doing a live maintenance, then like means if you are not really wearing personal protective equipment, then you are gone. We do not know when the worst case scenario comes. There is no point in worrying after the incident has happened. You do not have the capability to go back in the time frame and modify something and save the person who has already had a fatal incident on an R plus. So, what's the precaution which you have to do? Perform short circuit correctly, perform relay coordination properly, perform an R plus study, ensure that, like means to say, R plus boundary is marked properly at site, wear necessary personal protective equipments before opening the door of the switchgear. Okay. R plus study, the cost is small, the risk is huge. Save your life, remove the colleagues, save your life. So electrical accidents definitely is not going to give you the second chance or a second choice. Every R plus incident leaves behind a damaged equipment, which probably like a commercial loss, but lost lives, that is like I mean to say irrecoverable damage and many unanswered questions. So R plus study is just not a safety requirements. It's a moral responsibility, I believe, because it is your responsibility to protect you, your friends, colleagues, those who are just visiting your facility, right? So that's the reason why this is important. And like, what is R plus? I guess like we have already gone through IEEE 1584, but a quick update. A sudden release of electrical energy, temperature can go up to 35,000 degrees Celsius on the hot spot. It occurs in milliseconds. Extreme heat, intense light, pressure wave. So, extreme heat, severe burns, fatality, intense light, I mean, say permanent blindness, pressure wave, hearing damage, sharpnel injuries, right? So, it can be like, I mean, to say multiple things. So, going further, so R plus, it's deadly, but generally it is like means to say ignored. There are like means to say 30,000 plus R plus incidents every year, including many fatalities. At least 2,000 hospitalizations annually. This is OSA data, and probably like many of the informations are probably like means to say not comes to public because of like they hide the information, etc. Average treatment cost per victim, it is 500K to 750K USD. 80 percentage electrical injuries, 40 to 50 percentage of industrial accidents are in electrical maintenance that are linked to R plus. So this can result in lifelong disability or a death within fraction of seconds. So what are the industries at risk? Any industry which needs a live maintenance at risk. So steel industry, cement, power plants, oil and gas, data centers, or pharma, which is probably missing, where you feel like means to say you are doing a live maintenance, that's pretty much dangerous. So few real-time incident. It is one of the steel plant in Karnataka. So R plus occurred in electric arc furnace. So faulty breaker operating during switching. So there was two workers severely burned. Plant downtime is about 36 hours and production loss is about 3 to 4 crores Indian rupee. Lesson learned, no R plus study, PPE not rated for actual incident energy, switchgear not designed for arc. Like that means it's not arc rated switchgears. Incident 2, this is a thermal power plant, 220 kV switchgear and control relay panel. So it like means to say most of the times like means to say the rack in rack out of the breaker is probably like means to say results in one fatality, three critical injuries, shutdown of entire 500 megawatt generating unit, loss of about 8 to 10 crores. So lesson learned, there is no R plus boundary labels, there is no relay coordination study which is done. Workers are not aware of approaching this. Like this is another aluminum plant, similar incident. So what are the laws and standards says? Like Occupational Safety and Health Administration in USA, employees must provide a safe employers must provide a safe workplace for their employees. Non-compliance results in legal liability, heavy penalties, and shutdown. NFPA 70E, so mandates R plus risk assessment, define PPE categories. That's where like PPE is recommended by our NFPA 70E, not by IEEE 1584. It defines safe working practice and it also needs a recommends training. IEEE 1584 2018. This helps you to find out the incident energy and R plus boundary, based on which using NFPA you can recommend PPEs. So India to CEA, Factories Act 1948, National Building Code NBC. So what are the different PPE, personal protective equipment levels which it is there? So PPE category 1, up to 4 calories per centimeter square. Category 2, up to 8 calories per centimeter square. Category 3, up to 25 calories per centimeter square. Category 4, up to 40 calories per centimeter square. Beyond 40 calories per centimeter square incident energy, there is no proven tested personal protective equipments. There are manufacturers, those who claim, means they will be able to supply PPE even up to 100 calories per centimeter square. Only one warning which I can give: you wear 40 calories per centimeter square and doing nothing, stay there for a minute, then you can understand how much pain or how much uncomfort it is. So you cannot put up personal protective equipments for 100 calories per centimeter square and means you can ask the peoples to work at site. That's almost impossible. I would always strongly suggest you to limit personal protective equipments and the incident energy, and hence, of course, to less than 25 calories per centimeter square. There are companies those who limit the incident energy to 12 calories per centimeter square also. So there are multiple methods to limit the incident energy. One, limiting the short circuit current itself. Second one, limiting the duration, which is pretty much easy. Like there are multiple methods, like means to say maintenance switch, or probably means to say instantaneous settings. When you're going for a live maintenance, group settings, there are multiple things to achieve it. So few of the case study which we have done, it is including DCR plus studies. It's a 1200 megawatt solar plant, right, in Abu Dhabi, where we have done R plus studies. And it's probably done like a couple of years back. Means to say it is 380 kV, where there is no R plus study, but means to say your 33 kV, 400 volt, 420 volt, 660 volt at the inverter terminal, all these things. And the DC side, means to say DC panel side, this R plus study has been done. And some of the auxiliaries which are diesel generator which is running, means to say which we have done. So, means to say, what is the incident energy? Low voltage panels, it is less than 4 calories per centimeter square. But at 33 kV, the incident energy has gone beyond 40 calories per centimeter square. So, what we have recommended is don't do any live maintenance. It's a solar plant. No need to do live maintenance. Means if at all, if it is you will lose some energy, which means you will lose some money, but your life is more important than money. So no live maintenance. That's what our recommendations. And DC panels, it is less than 4 calories per centimeter square. So this is one pharma industry in Hyderabad. Typically, pharma industries needs this R plus studies, right? And means to say few cases that's what this is an interesting industry where means to say diesel generator case, they have transformers with the bus coupler open, one transformer which is feeding entire load with the bus coupler closed, and DG, all the cases which has been worked out. So means what to say, the DG case also becomes worst case for few of the MCCs that results in means to say higher PPE requirements, right? So this is again same thing. It's another project, CAE Husu. like I'm not really going to probably take much time.
So SKM, like it's a power tools for Windows. Like whenever we are talking about SKM, it's a power tool for Windows. So like whenever you are installed with your SKM software, like you cannot find SKM directly. So you have to find out the PTW, which is power tool for Windows. So by just searching on it, or you are having like a shortcut, so you can find out and you can just click and open the file location. So the shortcut will be available. So you can just click on that and open it. So your SKM will get open. Yeah. So I hope like my SKM is open. So once you are opened with the your new SKM, so it will be appear like this. So you have some more options, like you can create a new project or you can work with your old projects. So like right, so as of now, like I was going to create a new project. So how can we create a new project? So just go to project and we can like click on the new. So it will be give us where we want to share, like where we want to save our files. So the specific exact location, like we need to know about like where our project files and our results and TCC curves are stored. So we can like create open a new, like open a new file folder. So which is like SKM webinar, right? So master webinar. So we can open it. So here like SKM. So this arc flash webinar. So I will be like putting AW. So once I was opened, like I was redirected directly to the component editor. So in SKM, like there was two things. One is component editor, and one more thing, like it's a one line diagram. So like when we are talking about like the SKM, so we can like once we have created the SKM file, so you can directly go to open and your exact folder, you can find the project file over there. So you can click and your one line diagram page will be appeared. So it will be as of now it is like empty. So the thing what we are going to model today, like we are going to pretty like we are going to model 11 kV, like 11 kV voltage source, which from the feeding from the grid. So after that we are going to like see one transformer, which is like pretty much like 1500 kVA transformer. So which is like converting the voltage to 480 volt. So from there it is like using a motor source. So that is our end feeder. So like this data which we are like available at the end. So this what we are going to model at our SKM software. So like quickly we are going to model and we will be see like how can we generate the arc flash label, right? So first like how we can find, like we can select the grid, like you can able to see the screen. So this identifications over there, these are our components. Which components we want, we can find it over here and we can drag and drop. So our component will be available in the editor page. So now we are going to use the utility grid. So I'm just clicking on the utility. So my utility is up here. So like before, before like doing this, before doing this grid. So what we require, we have to identify what is the standard which we are going to follow. So we have to set up parameter standards. So we can set the parameters. So what is the standard? So you can find out here. So is it visible, right? So yeah. So application standard. So what is the standard? And see our IEC which I'm going to follow. So IEC I'm going to follow. So unit metric pretty much I'm working on. So wires, like wires, there is a AWG or a millimeter square. So I'll be going for millimeter square. So the system frequency is 50 Hz. If it is 60, we can select 60. Otherwise, like a cable sizing, what is the cable sizing? And what is the like length of the component names which we can obtain? So it can be restricted up to 14 or it can be like extended for 30 characteristics. So I can set the parameters and what is the report it has to be generated once it was done. So what is the online diagram parameters and other stuff? So TCC curve, what is the default curve pattern I have to use and the color. So this will be appear in my TCC curve, right? Yeah. So this is the standard I was fixed. So now I will be going to work on the modeling. So let me take a grid. So our grid is 11 kV system. So grid we have to model. So how can we go? So once our equipment is into the page. So once our equipment is into the single line diagram, so what we can do, we can right click. So you can right click and go to find and component editor. So what you can do, you can right click and go to find and component editor. You can find the component editor. So in this component editor, you can do the data. You can provide the data of the utility grid or your bus or your cables or your equipment. So all the equipments which you are going to work for a load flow or a relay coordination or for arc flash or a short circuit or motor acceleration. So which using the SKM software, you are going to model it here from here, right? So from here only you are going to model. So you want to enter the data. So like ETAP. So our SKM also having libraries for their equipments. So which you can take from the SKM's owner. So OEM. So you can raise a inquiry and you can get the help from the SKMs, right? So utility we pretty muchly know. So what is the utility data we are required? We are required a short circuit current. So what is the three-phase short circuit current? Let me assume three-phase short circuit current as a 350 MVA. Like so the MVA which we are talking about. So line to ground, which I was taken as a half of this. So 170 I will be taken. So R and X value, I will be keep this as it is. Otherwise, I will go with the assumption of 50 Hz frequency system. I can go with X by R as a 14. So after converting those data into R by X, so I will be getting some value. So I will be updating this. So once I was updated correctly, my data will be give no any errors. So if I am putting any wrong numbers, if I'm putting any wrong numbers, so if my modeling is not converged or any problem, so it will be give me a one. So you can find in the endpoint. So there is one column. So which is yeah. So which is the calculation zero sequence impedance is negative. So which is my parameters are not properly aligned. So once I was done with the parameter properly, so once clicking the update, so my system will not have any warnings or error, right? So now I want to go back to the online diagram. So I can approach the window part. So I can find the online diagram. So after grid, what we are going to model, we are going to model a cable. So I'm just keeping drag and drop the cable and just model the cable. So after this cable, what I'm going to do, I'm going to convert, take this from the library. So once clicking on the library, I will be I'll be getting much data. So in the cable part, I'm dealing with LV or MV. So MV, HV and MV, I'm working on it. So I will be converting it and I'm going to voltage level. I know I was going to work on the 11 kV system. So my voltage, it will be cable voltage will be 11 kV and above. So let me expand. So pretty much I can go with 15 kV. So 15,000 volt. So the cable what I'm going free here. So once I was double click on it, so it will be appear those data over here. So what is the length from the grid to the system station? So I will be considering as a 600 meter. So the cable a cable sizing I am considering the cable size as a 350 square cable, right? So I'm using two conductors. So these are my cable length. So once I was done with my cable parameters, so my positive and negative zero sequence impedance are available, R and X values. So if the system is new, like I have to use a tolerance right now as of now, like I'm not going to use any tolerance. So like now I was done with the cable part. So next what we have to do is we have to like model a protective device. So the protective device which I am considering as a relay with the CT. So like after the relay and CT, what we have to model? We have to model a breaker. So there will be a breaker available in the system. So after the breaker, we are having a 11 kV bus, right? So which we can connect it here. So the bus data. So now I have to done with like cable data. I was done. So the protected device I was not done. So after this bus data also was not done. So protected device. Let me come to the last one. So bus again, like I can double click on the equipment. So it will be take me to component editor. So in the component editor, I already told you like in the SQ we are having a library. So the library, yeah. So in the library you can find. So there are a lot of like buses already existing. So which is like there is a lot of buses which is already available. So switch gears. So like let me take a 1500 kVA switch gear. So which is like it's the current rating pretty muchly like I'm using a 1500 kVA system. So like the switchgear current which is limited to 75 amps. So it's approximately 100 amps. So I can go with more like 600 amps is enough for me. So square B, which I can double click. So the data can be appeared over here, component editor. So like you can see, so the data, the equipment category, and the manufacturer, those details already in the existing library, which I have taken. So after this, I was taken a like arc flash, you can see, once it was the equipment was directly taken, so it will be directly like the arc flash boundaries, like what is the box height, width, and depth, and the bus bar gaps, and what is the working distance, which is like with respect to standard. So like this all things which is already existing in a library file. So that will be appeared in my page. Yes. Right. So it will be appeared in my component editor. So like I was done. So once I was done with this, so what I can do, I can go to next equipment. So as of now, like we are done with, let me go to the online editor page. So now we was done with the bus, right? So next thing what we have to do, we have to model a outgoing feeder. So outgoing feeder, I will be taking like breaker. So after the breaker, there is a protective device like relay. So after the protective device, there was a cable which I am going to consider. I'm not this time. I'm not going to model this cable as much as. So what I'm going to do, I'm just copying the data from the existing like model. So I'm just going to use the same. So I will be like copy the parameter and I'm just pasting the parameter. So my parameters are updated over here. So the cable size, which is like I'm going to use 250 square mm with a single run. Okay. So cable ampacity, it is available, right? Yeah. So after this, what I am going to do, I'm done my cable modeling. So what I'm going to do, I'm going to next model my transformer. So you can see the transformer, I can pick and I can drop it. So in the transformer, again, right click and go to the component editor. So let me like model the entire system first. Then I will be like going to component editor. So next what we require, again, like we are going to connect the LV switchgear, which is MCC. We are going to connect it with the bus duct. So for the bus duct also, what we have to do, we have to like we have just give me a second. So what we have to do, we have to use a cable. So in the cable, like in the library, we will be using the bus duct. Yeah. So after this, what we have to do? So now we are going to connect with the LV breakers. Whenever we are having the incomer, there will be like breakers available. So I will be taking my LV breakers and I'm connecting it. So after my breaker, I'm directly going for a bus switchgear, which is like LV. I'm considering the release. Yeah. So after this, like I'm going to use 3 outgoing feeders, which is feeding to motor. So which like pretty much like I'm considering 250 HP motor and one 500 HP motor. So let me model the motors. So for a motor, like again, what I have to do is I have to have a LV breaker. So LV breakers, I know I'm having 3 switch gears. So let me take a breaker first. Yeah, and I will connect it. So after that, I'm having a cable which is connecting breaker, which is switch gear outgoing feeder to my motor. So after that, motor terminal. So let me pick a motor from here. So I'm just inserting my motors. Now I was done with my modeling part, right? So let me have it in a full screen. So my modeling is clear, right? Yeah. So let me grab the page. So what we are expected to model. So we have achieved those models in the scheme. So now like we are partially done with the component data also. So like what are the like data which we are missing is in the LV part and the transformer. So transformer, like I will be right click on this. So in the transformer also, like there is a library available. So from the library, if your transformer is fit or you're having library for your transformer from the OEM, so you can use it. So at the moment, like yeah. So at the moment, I will be like going with like my like values. So I know like I'm using 1500 kVA. So load like I will be considering 1500 kVA. So after that, the primary data and secondary. So primary, like I'm going to use delta star winding, so which is like rated voltage of LV, which I am considering as a 11 kV. So the bus voltage, which is connected, is also 11 kV. So the secondary, which is star grounded system. So in the star grounded system, like what is the voltage? Like I'm considering 480 volt. So 480 LV. So bus voltage will be also a 480. So after this, the taps, I'm not assuming any taps in the HVR LV. So like there is a tap. So I will be consider this as a like it has a DTC. So like so I'm not going to model the tap over here. So after like I was done with this, so I have to done a transformer impedance. So I can go to impedance page, transformer. So typical like what is the transformer I'm going to use? I'm going to use a dry type or oil type. So it will be like give me a typical value of the impedance of the transformer. So I'm just going to get a typical value of impedance and XVR ratio of transformer. So with respect to that value, automatically R percentage and X percentage will be reflected. So transformer also I'm not using any impedance. So after this, like in the neutral impedance. So if I'm just resisting any neutral current with NGR, so I will be modeling here. So like if I'm going to resist my like current, which is like with respect to 400 amps, so I'm going to consider the NGR. So the resistor which I am going to add it in the system is 0.69 ohms, right? So which will be like I will be getting this data. Yeah. So I'll be getting this data. So once like I was done, my transformer component modeling is done. So yeah. So after this, I have to model a cable. So like what I will do, I'll again go to component editor. So library, I'll be picking from LV. So 1 kV voltage, which is 1000 volt system with 3 square cable, sorry, 3 core cable plus ground. I'll be using the copper from a just give me a second. I'll be filter it with voltage. Yeah. So I'll be double click on it. So the data will be appeared over here. So again, like I have to provide the cable length. So this which I will be considering my transformer to switch here with respect to 300 meter. So the cable size which I am considering like around 150, 250 square So now I was getting my resistance and the reactance. So after that, you can see my ampacity is 2650. Like I'm having a current of transformer of like 1800. So what I have to do is I have to like increase the cable size as well as the run. So my design, like the design will be like this. If I'm considering the cables. So the cable ampacity is above our range. So we can go to next point. So the bus. So bus also I'm going to select from a library, which my bus voltage is 480, correct? So which I can go like I can select this Allen Berry. So by double click on it, or you can select and apply, we will be getting the data in the bus. So link library. So your data will be linked to your libraries. So arc flash data is like which is with respect to box height and box with box depth and gap and working distance will be like with respect to the library, it automatically appeared over here. So after this, now we have to model a motor cable. So motor also like what I'm going to do, I'm just going to copy paste the data. So I'm just copying and pasting the data. So let me just runs only like I'm going to go with minimum numbers of run with minimum square amount. So which is like I hope like it is enough for my system to handle the current from the motor. So now I can copy this data. I can paste it in the remaining cables. So now I was done with the cable data model. So after that, I have to done for a motor. So motors like motor also I'm going with the library. So 250 motor, the rating is 480, like 460 I can select. So 250 which I was expected to get. So in the 250 like I'm going with 4 pole. So double click, the data will be appear. So like I'm going to get it. I'm going to use like a two motors as a 250 square ohm, right? So 250 HP. So I will be copy this data and I will be pasting those datas in another motor. So the remaining one more motor. Yeah. So I will be like using 500 HP, which is also in the 460 voltage level. Okay. So I was like modeled with my motors. I was modeled with my cables. Now I was pending with my like protective device, which is breaker. In the terms of like release, we are talking about in the LV system. When we are talking about the HV system, so breakers are the protective like device which is going to isolate the faultier portion from the healthier portion. But the relays which are going to analyze the fault and which is going to like give a commands to the breaker, right? Yeah. So like let me have this. So I have like like have my existing settings. So what I will go, I will directly go to breaker. So I will take it from the library. So the protective device which I can use is LSI in the voltage level of 480. So I'm just selecting any one value. So which is like randomly like I'm selecting around 250 to 600 amps. So or I can go less, something around. So what is my breaker like? What is my motor rating? I have to identify. So on my 250 HP motor, which is like full load current is 281. So the another one motor is there, which is my 500 kV motor. So which I am going to use like the FLA of 553. So for this like for a two motors, I have to model with a 400 amps breaker is enough for me. So one more motor I can go with 800 amps breaker. So I can go to the library. So I can go with the LSIG in ABB. I can double click. So the data will be appear. So once the data will be appear, it will be asking me the settings. So our arc flash will be like the incident energy will be like what is the protected device and what is the protected time, which we are like we are isolating the fault from the system. So that will be like mainly for our arc flash. So yeah. So the settings which we can like put. So I am considering, yeah. So there is a voltage level like device voltage must be greater than the bus voltage. So what is my bus voltage is 480. So which device voltage it is telling? Let me check. So plex setting I will be consider 400. So the value, so which I will be assuming as per the calculation, the data which I have taken from the project. So I will be consider this and 633. So I will be like make the protection function off. So instantaneous I will be using 6 point. There is some error in the setting. Now I can, there is some error in the library file. What I will do, I will just get to other, yeah. So I was wrongly taken the wrong voltage. So what is the KVA like this once I was done? And now I don't have any errors. So what I can do, I can go to online page. So I can copy this and copy those data and paste it in another sheet. Why? Because these both are 250 HP motors. So the other motor, which is like, I have to use the rating. First of all, I have to select the library. So it's, so the library, like the voltage level and the current, like which I have to use it around 600 to 800. So I'll be using the 800 amps. So I will be double click and give apply. So it will be like provide some details. So I have to select the voltage level. So I will be selecting 480 volt, which I have considered for my switch gear. So the plug rating sensor 800, plug rating 800 I am setting. So for this, I am going to provide a setting of 0.88 and the time which I will be considering 12. Now I was done the protected device for the LV. Yeah. So after this, like I'm directly doing for 415 volt. So I will be like select the library and there will be like 1800 amps over there. So I will be going for 4000 ampere. Just give me a second. Yeah. So my voltage level is 480, right? And the current which I am considering 3000 amps, 480. So I can go with 1800. Now my protected device for LV is done. So the same way like I was model with the HV. So I'll be modeling the income or protected device. So which I'll be selecting from the library. So the relay which I'm using, an electronic relay, which is from ABB REF615, which like everyone like it is most of the members like know about this like protected device. So the CT ratio which I am considering 250. So the incomer CT ratio secondary is 1 amps. So the settings which I am considering like as a 5P, just give me a second. So the settings like which I am considering 3.5 with respect to the transformer. Now I was done my PD here, and one more device I was pending. So let us finish this and we directly move to the arc flash. How can we generate the arc flash? So the settings for this is like I'm considering 100 amps. Of the secondary is 0.1 amp. So 0.86, 0.54. So I'm considering 19 and the time delay as a minimum time delay. So now we were like done our modeling part. So now we can go to the arc flash and we will create a, like we can run our arc flash and we can create a level and we can conclude our section. So in the run, you can find the arc flash evaluation. So click on it. So it will be give you the standard. What is the arc flash standard and what is the fault current standard? Like arc flash standard IEEE like for 1584 2018, which is like already existing in the SKM, or it is like 15 to 800 kV arc flash analysis we have to done, or like less than 600 volt arc flash analysis we have to done, and what is the capacitive, like capacitor safe discharge voltage we have to use, and these data we will be like providing, and what is the unit what which we need, and what is the distance like incident energy unit, and what is the distance and boundary distance which we required, and what is the like fault current with respect to like maximum or minimum fault current. So those data we will be selecting over here in the study case, and by clicking on OK, so it will be directly run our arc flash study. So you can find these data. So that we are having like two buses. So let me like the bus data over here. So this is like from the SKM only, like we cannot zoom this, like we cannot make more zoom on it. So the bus name and protected device which we are using, what is the bus fault current, bus arc flash current, and protected device bolted fault, and what is the trip delay time, and what is the breaker operating time which we are considered, and what is the electrode configuration, it's a switchgear or MCC or a switchboard, it will be appeared here, what is the bridge like box with the and height and depth. These all data will be appeared. So along with the arc flash boundary, working distance, incident energy. So PPs. So we are done like we are having a two system. So for this two switch gear, we are going to create a like arc flash label. So we are going to go to customer label. So customize label. In this customize label, you can find like what are the device available and what is your PD. So you can find like you are having a lot of like standard label, so standard label templates. So in this template, like which template we want, so we can select it. So this our flash label will be our final objective. So this what we are expecting, and this what we are going to paste whenever we are going to work in the switchgear or switchboard in a live. So we have to aware like what is the incident energy and what is the working distance and what is the PP level we have to use, and what is the voltage of the switch gear. So what is the gloves we have to use, and what is the limited approach boundary, what is the restricted approach boundary, so what is the bus level. So these are for the identifications. So it will be appeared here. So once you are like get this data, so you can go to print. So it will be ask you like what are the device you want to print and how many numbers of copy you want to print. So in the 11K